So, hello students, welcome back to this new lecture. As we completed the, you can say, quadratic, right? So, the next chapter which comes in that series, or you can say in revision series, which we are doing crash course type, because we had not covered this in the previous lecture. So that is complex numbers. As you can see, today's our aim is to discuss the following topics: introduction, algebra of complex numbers, modulus and argument, and do some questions. So I hope to cover all this, but let's see how much we can do. We can do more than this or less than this. Okay, so without further ado, let's get started, guys. Yeah, the first thing is this complex number. So, what is a complex number? A complex number is basically of the form a plus ib. A complex number is of the form a plus ib, where a and b are real numbers. Let me on the slideshow so you'll be able to see it properly. Yeah. So complex number is of the form a plus ib. There are two types of complex numbers. That is real complex numbers and imaginary complex numbers. Now, this is just not just very good definition, you can say, just a way to classify the complex numbers. So here, real complex numbers. What are real complex numbers, guys? Where imaginary part is zero. Where imaginary part is zero. You can see here, imaginary part is b. B is 0. So when B is 0, the complex number will remain, that is A only. That is basically it's a real number. Correct? So complex numbers and imaginary complex number. Imaginary complex number means the real part will be 0. That means A will be equals to 0. Correct? So here you can see A is 0 and B is all real numbers. That means it is a purely imaginary number. So this imaginary complex numbers is also called purely imaginary number, and real complex numbers is also called purely real complex numbers. Right? So what we have next here, equality of complex numbers. Now, in algebra of complex numbers, as we studied real numbers scenarios, there is equality, there is addition, subtraction, multiplication, division. So same thing we are going to do in equality of complex numbers, or you can say in complex numbers. That is equality of complex numbers, addition of complex numbers, subtraction, multiplication, and division. Correct? So here we have equality of complex numbers. So let's say there are two complex numbers, a plus ib and c plus id. Just a second, guys. Yeah, so there are two complex numbers, a plus ib and c plus id. If we say that a plus ib is equals to c plus id, that means the real part is equal and the imaginary part is equal. That means what is the real part of a plus id? A. And what is the imaginary part of c plus id? It is c. So a will be equal to c and b will be equal to d. The imaginary part will be equal to imaginary part. Next, let's say example, if x plus iy equals to 3 minus 4i. So what does that this means, guys? This means y is equals to minus 4. X equals to 3 and y equals to minus 4. Correct? So let's see here, same thing by comparing real and imaginary parts. X equals to 3, y will be equals to minus 4. Very simple. Let's see the next one. Algebra of complex numbers. First, we are going to see the addition. Now, in addition of complex number, let's say we have two complex numbers, x1 plus iy1 and x2 plus iy2. So here, if there are two complex numbers, then if we try to add them, then the real part will get added and the imaginary part will get added, as simple as that. Right? So add the real part, and if we add imaginary parts, we can take the I common. So we'll get x1 plus x2 plus I times y1 plus y2. Same can be done for subtraction, right? Because addition and subtraction is not so different. Let's say z1 is 2 plus 3i, z2 is minus 4 plus 6i. And if I ask you to add z1 plus z2, so it will be, what will it be, Asha? We have to write the answer here. It's fill in the blanks type. So it will be 2 minus 4. So let me grab a pen. It will be 2 minus 4, which is minus 2, which is minus 2 plus 6i plus 3i, which is 9i. So our answer would be minus 2 plus 9i. Very simple, guys. Very basic calculations and all. Let's see the next one. Subtraction. Subtraction is also same thing. We just subtract the two numbers, right? No need to go through any details here, I think. So yeah, multiplication. Now multiplication is important because when we multiply two complex numbers, we are basically multiplying two brackets. That means when I multiply z1 and z2, that means I multiply a plus ib1 ka bracket with a2 plus ib2 ka bracket. So in normal way, the way we open the brackets, we can open it here also. That means we'll get a1 a2 plus ib1 b2 and I square. And we all know what is the value of I square. It is minus 1. What is the value of I square? It is minus 1. So if I square ka value is minus 1, then we can group the real parts together. That means a1, a2 minus b1, b2, and we can take I common from the imaginary parts. Correct? So what do we have here? Multiplication is over. The next is division. This is very important because many questions are asked on this concept also. Obviously, guys, it is important because if I am going to study complex numbers or for example, let's say we wanted to study maths, right? Normal algebra. We should know addition, subtraction, multiplication, and division. Similarly, we should know addition, subtraction, multiplication, and division of complex number also. So, in division of complex numbers, see, let me tell you, complex numbers are basically, we have defined them of the form a plus bi. The complex numbers are of the form a plus bi. So when we divide two complex numbers, they do not get into that form. That is a plus bi. Correct? They do not get in the form of a plus bi. So what do we do, guys? Let's see first, and then you'll understand. Here we rationalize. As you can see, this number a1 plus ib1 upon a2 plus ib2. They are not in the form of a plus bi. They are not in the form of a plus bi. So what do we do here, guys? We rationalize. Rationalize means multiply and divide by conjugate. So once we multiply and divide by conjugate, in denominator we'll see a plus ib into a minus ib, which is a square plus b square, a normal algebraic identity. So what do we have here, guys? In numerator we can multiply normally as we did in multiplication of complex numbers, and in denominator we'll get the formula a square minus b square. So what do we have here, guys? A square plus b square. Why? Because I square is minus 1. Because I square is minus 1. Now if we separate the denominator, then we'll get two parts. Obviously, guys, we don't need to remember these two parts because it is no way we can not approve, or you can say not really very important to remember this. Instead, you remember the process that every time I get two complex numbers, one upon the another, what do we do, guys? We rationalize. We rationalize. Correct? So yeah, next, what we have? Conjugate of complex number. What is conjugate of complex number? Conjugate of complex numbers is basically the imaginary part will be replaced or will be changing in sign. That means if here z equals to a plus bi is a complex number, what is the imaginary part? ib. So ib will be changing its sign from plus to minus, and the conjugate is denoted by z bar. You can see z ke upar bar, and it is read as z bar. So the imaginary part ka sign will change. IB say minus IB. I hope I am making sense. So Z and Z bar, right? So replace I with minus I. It's simple definition of conjugate of complex numbers. Properties of conjugate. Now, this is something very important and frequently asked in questions also. So, let's study the properties of conjugate numbers. So, let's say Z bar, a bar. So yeah, let's study the conjugate. If we take conjugate two times, correct? Obviously, we'll get the complex number itself, common sense way. So z bar equals to z bar, the whole bar is equals to z. Next, z plus z bar. If you notice, if we add z and z bar, the imaginary part iy will get cancelled and we'll get x plus x, which is equals to 2x, which is equal to 2x. So that means 2 times real part of x. Similarly, if we do z minus z bar, which is equals to 2 times imaginary part of z. It is 2I imaginary of z. Z equals to z bar. If in a sum we have been given z equals to z bar. So when those two can be equal, guys, those two can be equal only when z is purely real. That means z has only real part. Remember the first slide that we studied, right? Only real. That means z is having only the real part, that is a. Similarly, if z equals to minus z bar, or you can say z plus z bar equals to 0, that means z is purely imaginary, which means that real part of z is 0. That means a is 0 and b is non-zero. And next, the most important property you can say of complex numbers, not complex number, of conjugate, it is z bar equals to mod of z square. That is, if we multiply z and z bar, we have not studied modulus, we'll study, then we'll understand it more clearly. But if we multiply z and z bar, then what do we get, guys? We get real part ka square and imaginary part ka square. As you know, z and z bar are conjugate, so we get a plus ib into a minus ib, which is a square plus b square minus b square, but that I square becomes minus. Correct, guys? So this is an important property. Let's see the next. We can give the conjugate to both of them, correct? And same is for minus, same is for multiplication, same is for division. That means if we divide the complex number and then take conjugate is as good as taking conjugate and then dividing the numbers. Please, I'll repeat myself. If we divide the complex numbers and then take conjugate, it is as good as taking conjugate and then dividing the complex numbers. Okay, guys, just a second. I'll drink some water. 2 minutes. Yeah, so I hope you also drank some water. It's actually, when we keep talking, like my throat gets sore. That's why, and I have a problem in my throat also. So no worries, guys. Sorry for the delay. Let's see modulus of a complex number. Now, before understanding modulus and argument, I would like to talk to you about complex numbers. That okay, first we'll see modulus and then we'll talk about it. So modulus of a complex number. So if z is a complex number a plus ib, then its modulus is denoted by mod of z. Its modulus is denoted by mod of z. And what is the value of mod of z? It is under root of a square plus b square. It is under root of a square plus b square, which is basically under root of real part ka square plus imaginary part ka square. Correct? Next is obviously, guys, it's modulus and it's under root, so it is always greater than or equals to 0. Now, example, if z1 is 3 minus 4i, then what will be its modulus? Under root of 3 square plus minus 4 ka square, which is basically equals to 5. I hope we have you remember that we studied vectors, and modulus of a vector is taken in a similar way, right? That is, if a vector is 3 I cap minus 4 j cap, if a vector is 3 I cap minus 4 j cap, then that means its modulus of the vector, or you can say length of the vector, will be equals to under root of 3 square plus minus 4 square. So it is a very important observation here, which we need to study complex number, or we can basically use some results by connecting vectors with complex number. It's a very interesting part, guys. We'll cover it as we move forward in the chapter. So next, the order relation, this is not defined. That means there is no inequality in a complex number. That means that we cannot say one complex number is bigger than the other. That means if in a sum, like in a normal algebra, how we can say if 5 is greater than 2 or 7 is less than 10. Similarly, that inequality is not valid for complex numbers. Inequality is not valid for complex numbers, right? So there is no meaning of inequalities in complex numbers. Next is properties of modulus. Now let's see properties of modulus. If modulus of z is 0, implies z is 0. Correct, guys? Because then a and b both have to be 0. Next, modulus of z is equals to modulus of z bar. Because what is the difference in z and z bar? Only the sign change in imaginary part. It doesn't really affect the real part and imaginary part, as we have ultimately we have to square it. Correct? And the third property which we saw in conjugate, that is z bar equals to real part ka square plus imaginary part ka square. So if we square the modulus, then under root sign gets cancelled and we'll get a square plus b square, which is nothing but z into z bar. So this is the final property here, and it's very important, very nice property to use. Let's see the next. That is similar to conjugate. We can separate the modulus. That is mod of z1 z2 is equals to mod of z1 into mod of z2. Same is for division, and this is an important property here. Please pay attention. It is the same property which we studied in modulus of a bar plus b bar the whole square, if you remember. In vectors, what is the modulus of a vector plus b vector the whole square? It is a square plus b square plus 2a bar dot b bar. 2a vector dot b vector. But since here we do not have dot, what we have? Real part. z1 square plus z2 square plus 2 real part of z1 z2 bar. Please see here very carefully. It's real part of z1 and z2 bar, not z1 and z2. It is z1 and z2 bar. Similarly, z1 minus z2 में खाली minus का difference. If we add these two, the real part, or this 2 times real minus 2 times real, will get cancelled, and we'll get 2 times z1 square plus z2 square. Now, this is an interesting property. Sometimes directly questions are asked on this, which is modulus of a z1 minus b z2 the whole square plus b z1 minus a z2 the whole square. Right? What does that mean, guys? We have to square and add. So if we square and add, then finally we'll get this result. You can try it at your home by using this property 7. If we use property 7 here, you can see we can use property 7 here. Right? Just we have a and b. So a and b are constant. Anyways, it doesn't make any difference. As you can see here, a and b belongs to real numbers. Correct? So this was a question asked directly in 90s JEE, but we study now as a standard result. Let's see the next, which is express the following in the form of a plus ip. So now we are in the this one, you can say solving part. So for the solving part, let's see express the following in the form of a plus ib. So it's very simple, guys. What do we do? This is minus 5 upon 8. What is the value of I square? It's minus 1. So it's 5 upon 8. It's 5 upon 8. This is my answer. Let's see the next one. This is a very nice question here, guys. Why am I saying very nice question? Because here we'll use the addition, subtraction, multiplication, and division, all of them in complex number. So before this is a division of complex numbers. So let us first multiply or simplify the denominator. So if we try to simplify the denominator, in numerator it will remain same. In denominator, if I multiply it, I'll get 4 to the 8 minus 6i plus 12i minus 9i square. Now here we can group this because 8 and 9i square. 9i square, I square is minus 1. So what do we have here? We get 4 plus 3i upon 8 plus 9, 17 plus 6i. 8 plus 9, 17 plus 6i. Now we have simplified the denominator, so we need to multiply and divide. What do we multiply and divide by? Conjugate. 17 minus 6i upon 17 minus 6i. So what do we do here, guys? We again multiply the numerator, which is 17 4 are 68 minus 24i plus 17 3s are 51i minus 18i square. And in denominator, what do we have, guys? A square plus b square. That is 17 square, which is 289 plus b square, 36. So finally, what do we have here, guys? Upper again, we can add these two. That is 68 and 18 square. I square is minus 1. So we can add 68 plus 18, which is 76 plus 51 minus 24. 51 minus 24. So I think it is 51 minus 24. So what is it, guys? 24, 34, 44, 40, 34, 44, 27. I upon 289 plus 36. So here we have 5, 8, 9, 10, 11, 12. 1 carry, 325. This is my final answer. If you want to write the answer, we can write it like this, as the form of a complex number, which is 76 upon 325 plus 27 upon 325i. It is a plus bi format. Just a second, guys. I'll drink some water. Till then, you can solve this question. Yeah, guys, sorry for the wait. I hope you have done this question. What does the question says? Don't get confused, guys. Many a times complex numbers is given like a coordinate because we have not studied complex number in coordinate geometry. We'll study just in some time. So complex numbers can be given in terms of coordinates, but that basically means this z is equals to cos theta plus I sine theta. Cos theta plus iota sine theta. So we need to find z minus 1 by z. So first, let us find 1 by z. 1 by z is, I am writing cos as c and sine as I. So what do we have to do? We have to multiply and divide by conjugate. We have to multiply and divide by conjugate. So we get cos minus I sine upon denominator में cos square plus sine square, right? Very simple, guys. So we have cos square upon cos square plus sine square minus I times sine upon, sorry, here we have cos. So minus I times sine upon cos square plus sine square. Correct? This is 1 by z. So what is the value of z minus 1 by z? Z minus 1 by z is equals to cos plus I sine, cos plus I sine minus cos upon cos square plus sine square plus I sine upon cos square plus sine square. So what do we have here, guys? Let us group imaginary or real parts together. So cos minus cos upon cos square plus sine square plus we can take I common sine plus sine upon cos square plus sine square is my answer. Let's move to the next. This one. This is a fairly simple question, guys. Let's see what we are given. We are given z equals to, and we have to find z square. So we all know how to find a plus b the whole square. So yeah, from here directly see there are two methods, guys. One method which I'm going to show is we get z square. What is z square? Is 2 minus 3i the whole square. We open this bracket a square plus 2ab plus b square, and then we do LHS equals to something which is equals to RHS. Now, one of the method which I personally like, and we will use that method in matrices chapter as well, that is, we can write z minus 2 is equals to minus 3i. Now we can square the both sides and we'll get our answer. See, what is z minus 2 the whole square? It is z square minus 4z plus 4. This is 9i square. What is 9i square? Minus 9. So we get z square minus 4z minus 9 is the raya, so plus 13 equals to 0. Hence proved. This method is very effective when we have higher powers. That means if someone asks to find me an equation z raised to 4 minus z square plus 9, something like that. So this we cannot, like, we obviously, guys, we can do 4 power also by using this method, but this one is pretty useful and pretty time saving, I would say. And if it's time saving, it's our method because यही में तो टाइम सेव करना ही पड़ता है. Got it? So yeah, let's see the next one. This is a nice question. I personally like this question very much because trigonometry is involved here. So okay, what do we have here? We have to show that this is equals to 4x squared. That means we have to get the value of x. And if we want to get the value of x, we need to compare the two, you can say, complex numbers on left hand side and right hand side. And by equality of complex numbers, we can get the value of x. We can get the value of x. The first denominator, let us simplify it. 1 plus cos, 1 plus cos plus I sine. Multiply and divide by conjugate. So 1 plus cos minus I sine upon 1 plus cos minus I sine. So numerator we get 1 plus cos minus I sine upon 1 plus cos square plus sine square, right? Then what do we have here, guys? 1 plus cos minus I sine upon a square plus 2ab plus b square plus sine square. What is this? Cos square plus sine square? Cos square plus sine square is 1. And that one with this one will get added. So we'll get 1 plus cos minus I sine upon 2 plus 2 cos. So here we can also simplify it further. We can use the half angle formula. So 1 plus cos is 2 cos square minus I 2 sine cos upon. Denominator में same 2 into 1 plus cos, which is 2 cos square. We can cancel out the 2's and we can split. So we'll get cos square minus I sine cos upon 2 cos square upon 2 cos square. So this and this will get cancelled. One of the cos will get cancelled. 1 plus cos is 2 cos square. So this, I think this the whole will get cancelled. So we'll get 1 by 2 minus I by 2 into tan. Remember, we use half angle formula, theta by 2. So this is the value of x plus iy. So by equality of complex numbers, what is x equals to? X equals to half. So if we square on both the sides, we'll get x square equals to 1 by 4. That means 4x equals to 1. That 4x square equals to 1. That means 4x square minus 1 equals to 0. We got our answer. Correct, guys? I hope it is clear. A good question where some trigonometry is involved. Let's see the next. This one. This is also a very classic question, you can say, guys. Very classic question. So, what do we have here? What do we have here? Classic question. Same thing, guys. We want the value of x and y, or you can say a and b, and then we can easily prove this, right? We can easily prove this. So to get the value of x and y, here we have cube root. So if we cube on both the sides, I'll get x minus iy is equals to a minus ib the whole cube. So this is a minus b the whole cube. It is a cube minus 3a square b plus 3ab square plus b cube. Now what is I square? I square is minus 1. So what do we have here, guys? A cube minus 3ab square plus we take I common and we'll get b cube minus 3a square b. Right? This is equals to x minus iy. So by equality of complex numbers, what is the value of x? It is a cube minus 3ab square. What is the value of y? It's b cube minus 3a square b. We can take a common, so we'll get a square minus 3b square. Similarly, here we can take b common, we get b square minus 3a square. B square minus 3a square. So here we can take x a down. So we'll get x by a equals to a square minus 3b square. Similarly here y by b will be equals to b square minus 3a square. Now we want x upon a plus y upon b. That means we'll add these two equations. So if we try to add these equations, what do we have? We'll have x upon a plus y upon b is equal to here. You can see a square minus 3a square. Oh, guys. Sorry. This will be minus. So it will be minus b cube I cube. So I cube is minus I. So plus b cube I cube is minus I. I think we have done correct, but I think not also. Did we made some error? A cube minus 3a square b plus 3ab square minus b cube I cube. I cube is minus I. We get plus. So we got a cube Correct. This is x minus iy. So this is basically, yeah, made a slight error here, guys. So basically the error was it is minus yi. So if it is minus yi, this will be change in sign. The 3a square b minus b cube. So we can take b common, 3a square minus b square. This will be 3a square minus b square. So if we add, we'll get 4a square minus 4b square, which we can take 4 common, a square minus b square, which is a required, and this is hence proved. So let's see the next sum, or you can say next topic. The thing which I was talking about to you guys is same thing that we are going to talk about here. That is, we can express a complex number as a coordinate. But if we try to express the complex number as a coordinate, then we need an xy plane. Not exactly an xy plane, guys, because in xy plane only real numbers can plot it. It is real x is real numbers, y axis is real numbers. But here we have complex numbers. So to plot the complex numbers on the, you can say, a plane, 2D plane. That plane is called Argand's plane. That plane is called Argand's plane. So Argand's plane is a plane where the horizontal axis, or not, it is not called x-axis, correct? But obviously, guys, आदत तो अपना x axis का ही है. So the horizontal axis is called real axis, where the real part of complex number is plotted, and the vertical axis is the y-axis, where imaginary part of the complex number is plotted. So yeah, that plane is called Argand's plane or a complex plane, where we can place our complex number as coordinates. Now, guys, please try to understand it is nothing, zero difference between our xy plane and this Argand's plane. It's just a name where x-axis is the real axis, y-axis is the imaginary axis. Correct? Everything remains the same, A to Z. Correct? So this thing we talked about, let's see. Let's study the modulus of complex number with respect to Argand plane in detail. So let's say this modulus, as we know all this, right? Modulus is under root of real part ka square plus imaginary part ka square. So we have all known this property, amplitude. Now, here is the main thing that we need to talk. Amplitude means, guys, have you, like, do you all remember the polar coordinates? Do you all remember the polar coordinates? Polar coordinates where we join the point with origin and the angle made by that segment with positive x-axis measured anti-clockwise. Measured anti-clockwise was our theta. The same is amplitude or argument with a little bit of difference, which we'll study right after this. So let's say this is our Argand's plane and we have a point P. These you can see the notation. A point is denoted with bracket में उसका complex number. So P bracket Z. P bracket Z. So let's say we have a point P. If we draw the origin and if we drop the perpendicular, we'll get this angle theta, which is called amplitude. And you can see this here, the important part I was talking about. I highlighted it here just now, that in this case, the argument should lie between minus pi to pi. The argument should lie between minus pi to pi. The argument should lie between minus pi to pi. That means what are the quadrants of argument? 180 in clockwise, 180 in anti-clockwise. Correct? I hope I am very clear about this. This is a very general confusion which happens among students. So please make sure you avoid it. Let's see the next. Z plus xiy lies on negative x-axis. What is the amplitude of z? A very simple question for your guys. If z lies on negative x-axis, that means z lies here. Why this line came? Just a second. Let me erase it. Z lies here. So that means if we join with origin, we'll get this. And this is the amplitude, which is pi. Which is pi. Next, if this, let me end the slideshow. So I think that's it for today, guys. Thank you all for joining. Sorry, I didn't see the time. So sorry for taking some extra time. But yeah, that's it for today, guys. We'll meet next time. Everyone, bye, guys. Everyone, take care. Ta-ta.